Hello, everyone.
No.
Good afternoon. Nope. Oh, hello. A bleep. Hello, folks. Good evening, good afternoon, good morning, wherever you are around the world. I am Juliana Fagiardini, and today I'm your host. We will have Lukas Sismis presenting this April webinar about DPDK support on Suricata. And before we get started, as usual, a few words about Suricata and OISF. As many of you know, OISF stands for Open Information Security Foundation, and the OISF is a US 501c3 nonprofit organization that ensures that Suricata remains world-class and open source. We are dedicated to preserving the integrity of open source security technologies and the communities that keep them thriving. And our team and our community includes world-class security and nonprofit experts, programmers, and industry leaders dedicated to open source security technologies. Our funding comes from donations. So if you work for a company that uses Suricata or is interested in integrating Suricata in one of your solutions, please reach out to us. Maybe you could become a consortium member. Today, as I said, we have Lukas Sismis. He is part of the OISF core team member. As I've mentioned, he is the youngest. I am just a bit older than him in the team. He is a Ph.D. student at the Faculty of Information Technologies at Brno University of Technology and a researcher at CESNet. He is the contributor of the Suricata 7 DPDK support, which you all are very interested about, I'm sure. And he is interested in accelerating Suricata's performance either through hardware-assisted or software-based means. With no more to say, I pass the word back to you, Lukas. Have a great presentation, and thank you for being here with us today.
All right. Thank you, Juliana, for your introduction. Hello, folks. Let me share the screen to start off with a presentation. All right.
It's showing fine.
All right, so today's webinar
Lukas,
is...
Sorry for interrupting you. It's just one thing that I forgot to say. Folks, as usual, we have our Q&A channel. So if you have any questions, do share them in the Q&A channel, and we will make sure to read them and answer by the end of the webinar, okay? Thank you, and sorry.
Sorry. Okay, thank you, Juliana, for your addition. So today's webinar will be about Suricata and DPDK, and hopefully everything you need to know to have Suricata running with DPDK, even though you don't know much about DPDK. My name is Lukas Sismis. As Juliana mentioned, I'm the Suricata team member primarily and PhD student as well as research at CESNet. Today, we will talk about general Suricata overview, but as I can assume, you've probably already heard about the Suricata. So I'll rather introduce you to DPDK, and then we'll just go over some demo that I have prepared. All right, so you would essentially, Suricata is a sensor that goes over traffic. You've probably seen this image before. Suricata analyzes the traffic and produces some alerts based on some signatures. It can not only do that, but it can also monitor traffic and also export flow information, but also extract metadata and files of the traffic so that you have it available for later analysis. Suricata can also record PCAPs, either triggered by rules or you can have full packet capture. With regards to signatures, it can do many different things. How it can detect the signatures within the traffic. But one of those can be, you can also detect different alerts in between flows. So you can have more clients communicating, and if you see some weird traffic in between them, you can also raise an alert based on that. It can also have data sets, but and that essentially optimizes the way Suricata is used. But today's webinar will be about how Suricata receives traffic. But before we'll go into that, I wanted to show you how Suricata actually processes the traffic, what's the architecture of Suricata. So when you have a Suricata application, in that application you have multiple threads, and those threads are either management threads or packet processing threads. Packet processing threads are called workers in Suricata, and to these threads, packets are delivered from the network interface. Now, what is happening within that packet processing threads? Basically, everything that Suricata does. So when you have one packet processing thread, it contains multiple modules, and within those modules, different things are done. The first module that is the capture module, and an example of a capture module is can be AF packet, PF ring, NetMap, NetAttack, and DPDK. So basically, capture module is how you receive traffic from the, let's say, outside world to your processing thread. Then when the packet is received in that capture module, then Suricata passes the packet to the decode module, where the packet is decoded into VLAN, IP address, UDP, TCP ports, and etc. Then when this packet is decoded, it goes through the detection phase, detection module, where it's kind of matched against the signatures with IP matching, content matching, and some other basically fields as well. And when something is matched, or if not even if in network monitoring, it doesn't even require any rules. Like the last stage of the processing is the output module, where basically, let's say the flow information is exported to these common output files, or the result of the detection phase is exported to these common output files. And but this webinar is really about the capture module and DPDK, so how we receive the traffic. Now, what is DPDK? It's Data Plane Development Kit. It's basically, in a very brief term, it's a set of optimized open source libraries to speed up packet processing workloads. It's open source project governed by Linux Foundation. Previously, it was governed by Intel, but then it was passed to Linux Foundation. Now, contributors to DPDK are all over the world, although the main ones are, I think, Intel, NVIDIA, maybe Marvel, and some folks like that. Now, if we compare capture modules, AF packet, NetMap, PF ring, DPDK, why is DPDK different? I think there are two main points, and that is kernel bypass. In DPDK, the packet doesn't go through the kernel, as we will see, and the way DPDK receives packets from the NIC is by polling the NIC for new packets, whereas in other capture modules, it's provided by interrupts. We'll go over that as well. And now, why should you consider using DPDK with Suricata? It's essentially, as I mentioned, it's focused on improving packet processing performance, and it can add, let's say, up to 20%, but it really depends on the setup and the traffic, on the rules you use, on the hardware you have. So maybe in some cases, it might be even more than 20% of additional performance. In IDS mode, we don't usually care much about the latency, but DPDK might have another positive effect on latency in IPS modes. So compared to standard modes like AF packet, it can reduce latency as well. Now, here I wanted to compare how packets are received by the capture module. AF packet is the default capture module that you would use with Suricata, and DPDK is the thing that we are talking about today. In AF packet, which is on the left, you basically see NIC on the top left corner. It receives packet, then the packet is passed to the NIC driver, and as it arrives, the NIC driver pushes the packet to the buffer. Then this packet is stored within that buffer, but the NIC driver also sends an interrupt to the CPU core, like, hey, you got a packet in that buffer. Now, when CPU core notices this interrupt, it will call an interrupt handler, which is, I guess, essentially a callback, which will take that packet off the buffer and push it towards the application. As you can see, all these things are happening in the kernel space. This is very simplified diagram of what's going on in the kernel. There's a lot more going on in the kernel, especially within that interrupt handler case. And then the packet is delivered to the application. Whereas in DPDK, we essentially bypass the kernel space. Now, how is that possible? In DPDK, we have special DPDK pole mode drivers, which basically can communicate with the hardware, with the NIC from the user space. But these drivers they essentially allow us for packets to not go through the kernel space. But if we would have drivers programmed for different hardware, then our application would probably be kind of tied to that hardware, and it would be hardly portable. That's why we have DPDK and kind of a form of abstraction, which kind of divides the operation of the application and the driver. And in DPDK, we also have environment abstraction layer, which does the abstraction for us. It it creates an environment for us for our application to be portable from one environment to another environment, while also facilitates the communication between the NIC and the pole mode driver. So essentially, we then only work with a special DPDK PMD with our application and don't care about the rest. The pole mode driver essentially pulls the packet all the time. Our application needs to call this driver every time it wants to receive the packet. And in DPDK, it's always, we are always asking, Henning, do you have any new packets? And if it does, then the packets are returned to us. This kind of process is a lot more performant, but also it means that we are constantly going in cycles and asking for new packets. So that might be CPU intensive a bit. Okay. So this was essentially how what's different between the AF packet and DPDK. The main reason, the main difference is that the packets don't go through the kernel, and we constantly ask for new packets. The NIC. I've prepared two small kind of demos, one with virtual machine and one with physical machine. Virtual machine runs Ubuntu 22.04 server with virtual NICs. That's essentially to kind of, by having two kind of machines, I wanted to show you that DPDK can be set up in both environments, and also wanted to point out maybe some little differences in between the distributions of the Linux, let's say, and some tips and tricks on individual operating systems. With the physical machine, there will be also, let's say, a configuration process involved, meaning the physical machine is also, let's say, connected to kind of like live network, where we will also configure Suricata to with certain parameters to make sure we are up and running and not losing any packets, essentially. All right. Yeah, let's go. Demo. We will start with the Ubuntu with the virtual machine. Essentially, what we will want to do is to compile it from scratch. I think this can be helpful for folks who didn't compile Suricata yet. Essentially, the first thing that I want to do is to install all the required dependencies for Suricata. When this will be done, we'll also install, DPDK and DPDK development packages. Let's try. Of course, this is a demo, so something must go wrong. Let's try to update and upgrade. So let's try again.
If nothing goes wrong, then it's not a demo. It's
right.
just fake.
Okay, seems like we are up and running. So this is installed now. Those are kind of the required packages. Now let's install the DPDK as well. DPDK is provided in Ubuntu repository already. It's in Ubuntu, from Ubuntu 20. You have at least, I think in Ubuntu 20, you have DPDK 19. In Ubuntu 22, you have DPDK 21. The release cycle of DPDK is each year there is one major release, and 11th version of kind of like 1911, 2011 is the kind of the LTS, long-term support version. It seems like we have DPDK installed. Now let's check it with package config. Package config is for managing the libraries. So let's see. Yes, we got version 21.11, and the next thing for Suricata to compile, we need cargo install. We need cpine gen, so we'll install it with cargo, and then we will need to export this kind of binary to our path environment. We will see that in a second. So yeah, DPDK is very stable in releasing each year, and essentially it releases at least 3 times a year a minor release, usually every 3 to 4 months. And for the distributions or operating system that don't have DPDK compile or included in their repositories, I've also kind of prepared a variant for that. On that physical machine, we will also compile DPDK just to show that it's really easy. If it's missing in your distribution, it's not really an issue, and you can easily compile it and install it yourself. Currently, DPDK is not included in Suricata repositories, but I think it should be. When 7 is out, I don't think you should even need to compile it yourself. It will be probably included already in the package itself. So it's almost done. It just needs a little bit more of time. And now we will add it to the path. While we are waiting, I will clone the Suricata repository, just so we are efficient with our time. Time is sparse. So that's cloning. And that's cloning of the official GitHub repository. All right. Cargo already warned us that we should add this path to the our path variable. And so I'll do it. This command will add it basically to your bash rc, and that's the kind of script from where you can, which is always loaded when you log in. But for now, we will just also export it directly. Let's see, is the, yes, the Suricata is already cloned, so we can enter it. And what you want to do now is to bundle all dependencies. In this case, it essentially means bundling libhtp library, and now we can do kind of initialize our working environment with Autogen. For build process, Suricata uses libtools and kind of essential steps for compiling libtool projects is Autogen and configure. Configure script is like what you want to include in your build. In our build, I want to include DPDK. This will be kind of the minimal configuration. If I would be installing this on a machine, then I would add some additional configure parameters. But for now, I think enable DPDK is how you enable DPDK in your build, and you are good to go. When I scroll up a bit, I can verify that Suricata configuration has packet support, that's the default, and DPDK support, that's the important part today. The other thing you can also check, but for now we are good to go because it's enabled, and now we can essentially compile it. Before we run Suricata with DPDK, I think we can proceed to also verify that our DPDK installation has gone really successfully, not only by checking the package config, but also by kind of listing the DPDK applications. And in these applications, I can see 3 essential applications that you will need to use, and that is essentially DPDK dev-bind, which with which you work with your devices, with your network interface cards, DPDK huge pages for kind of allocating this memory pages in your memory, because DPDK essentially uses those to be more effective. I don't want to go into too much detail, but the default Linux distributions uses memory pages of size 2 kilobytes, or 4 kilobytes. But in DPDK, as you want to minimize the what you need to do with your you want to minimize the process of looking up the individual pages of your system. So that's why huge pages exist. When you have an application that has a lot of data, you want to store it in bigger chunks of memory, and those that's what huge pages are for. So we will use a huge pages script, and we will use test PMD scripts to that's the essential DPDK verification tool. If something is not working and you are not able to reproduce it in the test PMD application, then it's probably something wrong with you. With DPDK dev-bind, you can dash s as a status. You can see that we have 3 devices here, and it has 8000 driver. 8000 driver is a driver that's not supported by DPDK natively. What you need to do is to bind a different driver to this virtual interface so that DPDK can work with that. What that means is you can either use VFIO PCIe driver, Or there is another driver that's called, I think, let's try it. I need to invoke it. Yes, I was correct. So when I now list it with the mobprobe command, I invoke the second driver. Now it's in the list as well, and I can essentially link it to the driver, and that can be done by sudo dpdk dev bind. I'll press -b as bind uio pci generic, and now you cannot use the interface name because this is kind of the kernel thing. When you are in the DPDK, you essentially bypass kernel. And when you bypass kernel, you only have the PCIe address. So you need to enter your PCIe address of the device you want to bind. And now when we verify that, we have a line which says network devices using DPDK compatible driver. And now we have our interface bound to this interface. Okay, Suricata is compiled, so we are ready, but let's first also try it with the test PMD. So we got huge pages. Also the S is like a status. We see that we don't have any huge pages at the moment. So we want to allocate some. The help is really helpful. So let's say we want to set up 1 GB of huge pages. And when we go to status of the huge pages, we now see that we have 512 pages of 2 MB of size, which totals to 1 GB. Okay. Now that we have our huge pages, it's time to test it with test PMD command. Currently, in this VM, I don't have it wired with anything special. I'll just use A as an allow. Let's say by allow, you're kind of only allowing this interface to be used with this application. You're kind of not allowing other links to be used with this application. So yeah, let's allow only this. And I think it's a bit essential to go over these parameters with DPDK applications. The usual way how parameters or command line parameters are structured is that in the first place, you have environment abstraction layer parameters. That's the kind of the envelope that's where the DPDK application lives. And then you put 2 dashes, and that's kind of like after these 2 dashes, the application parameters will go. With test EMD, we are essentially saying that we will work in interactive mode, which means we will directly control the test PMD application. Now, I'm not sure why, but in this virtual environment on my laptop, it takes some time to load the application, but as we can see, it started to load. We will see. Let's check how the Suricata is doing. Suricata has compiled successfully, so I'm not gonna install it. I'm just gonna run it just to make sure we have set it up correctly. I'll use directly the configuration file. That's Suricata YAML. And when we search for DPDK section, we have exactly what I've discussed just previously, that those are the EL environment abstraction layer parameters. You could have the prototype, you could have the A, as I mentioned, you could have it like this. But in this case, I mean, it's not really required, but it's always a good idea to isolate the mix that you want to use. And the second part of the DPDK section covers the interfaces that we want to configure. In this case, we got the first item is the interface, but it's the PCI address of the interface was not 3B, but I think 008. Let's see. Yes, that's it. Yeah, we see that we are already in the test PMD application. So we would be able to do the start, stop, and quit. The test PMD application, what it does, it's kind of the, as I said, essential testing application to test whether your NIC behaves correctly. But in its simplest form, it basically just forwards packets of one interface to the other and vice versa. But in this case, we don't have it wired with with the second pair. It was just a test that our application is running. We will test it with Suricata as well. Well, when you are setting up the DPDK in Suricata, I think you always want to specify the number of threads that you want to use. And the other settings, I think we can leave as is for now. Let's see, set CPU affinity, and we want to set CPU affinity, as we will see in a second on the physical machine. If you don't do it, all threads will just end up on the first core. So we enabled 2 worker threads. So I'm setting this to 2 CPU cores. And so I think it should be ready to go. And our binary is in source Suricata. I want to use with the C parameter the configuration file. I don't want to use any rules currently with a capital S. I will be very verbose, and my logs will be stored in the temporary directory. I did something wrong, doesn't matter. Let's see the error. Okay, my other application is not. Okay. I'm missing the run mode. That's the most important thing. I need to tell Suricata basically which capture interface I want to use, because I could use IF packet, I could use DPDK like this, IF packet, but today we'll use DPDK. And now the application is starting. It produces a lot of output because I set it to do so, and it should load within a minute or two. In your environment, especially on physical machine, it definitely should not take this long. Okay, that's why I wanted to show you this kind of in virtual environments, at least with the adapters I've tried it with. You cannot set more than 1 worker, and that's kind of limiting for us. and it's not supported within those network adapters. So that's kind of pity. So for now, we will set it to one worker only, and we will try to run it. Okay. Considering hopefully this will run in a minute, let's probably move to the physical machine. We are currently here. I already have Suricata clones, but I don't have it compiled just to be on, like, just to start from the beginning. In this directory, let's say on this physical machine, this is Oracle Linux Server 8.7, like the software distribution. And let's say DPDK is not included. So let's compile it really quickly. It's using, instead of make, it's using Meson and Ninja as a tools. So let's install them. When you install just the Meson, then the Ninja is automatically installed as well. All right, this is the Suricata virtual machine, the Ubuntu one. We see that it's already started. It's all good. And now we would be running Suricata on Ubuntu machine. So that's all good. This also already received some packet. Okay, so we got Meson installed. And in this server, we have Intel NIC and Mellanox or NVIDIA NIC. I'll use a Meson command to set up the build directory. This essentially says that I will use prefix for installation /user directly. By default is installed in /user/local, but from my experience, it's easier to just set it to /user because it's easier found by the build services, let's say. But as I mentioned, in the server, I have a Mellanox card. And what I found, or what I want to check from the Meson output, is that I have my Intel driver E4P enabled and the Mellanox MLX5 driver enabled. I will look into drivers enabled, and I4P is there, but I don't see Mellanox. And that's because it's in between, like in skipped content, because it's missing some dependencies. So I want to install the Mellanox dependencies just to be just to have it included in my compilation. That's one thing that you need to be careful of. Now that it's installed, I'll remove my original build directory and configure the build directory again. Now it should include also the Mellanox driver for my network interface card. And now that it is included, I don't see it anymore in the skipped content, and I should check it in my drivers enabled. I see it's in my Mellanox enabled as well. All right, so since this is enabled, I'll just compile it with Ninja command, and I'll install it directly in one command. So this is how you would, this command compiles it, and the second command installs the DPDK. This might take a while, so let's look into how we are doing with Suricata. This is again a cloned repository from the OISF GitHub. Now let's install the required dependencies. On Oracle Linux, it looks something like this. I've installed these essential dependencies from which, without which Suricata wouldn't compile. And I also added, or will also add, Hyperscan to make sure our detection module is faster than with the default detection algorithms. So yeah, I would also recommend you to enable Hyperscan in your build. I will see that in a minute. Let's see. Let's see how is Ninja doing. Ninja is almost finished with DPDK compilation. This is the Hyperscan installation. Now we have it installed. We essentially want to do the same thing as in the Ubuntu. We want to install the cbindgen with cargo. And on this machine, I've already exported the path to the cbindgen, so I don't need to do that, but that would be basically export path commands as you've seen in the Ubuntu. Now, we see that DPDK is compiled and installed. This essentially confirms it. Now let's confirm it with at least the package config command. We see that we have 2211. When we look into its status, you will see that I cloned the DPDK repository and then checked out to the v22.11 branch or tag to make sure I have DPDK version, the version that I mentioned, 22. Okay, we see that cbindgen is installed, so we can essentially bundle autogen and configure the Suricata. Basically, the steps you've seen previously. I'll just quickly go over this. And then we will compile Suricata. While we wait, okay. So this is configuring. We will also do the make command, but in this case, we'll still not install Suricata because just kind of save time. We see that in our configuration, again, we have AF packet enabled, DPDK support. That's the thing that we enabled with the enable DPDK. And also, as we've installed also the Hyperscan, we also have it enabled. So that's why we have it. And now let's compile it. We have 10 cores on this machine, and let's say physical cores, so it will be a little quicker than in the virtual machine. Let's try running DPDK devbind on this machine, just to kind of see what's here. And again, here we see that network devices using kernel driver. We see there is one 6710. I didn't reverse all my changes to the default kind of settings, so that's why it's split in between this. But we see Intel card here with E40E driver, and then Mellanox or NVIDIA card that contains MLX5 driver. This is one interesting thing with Mellanox or NVIDIA drivers. They have bifurcated drivers. Essentially, these drivers can work both with kernel and DPDK. The thing I did with the virtual interface, that I was binding it to the IGB driver. You don't need to do this with Mellanox drivers. It will just work directly as is. You don't need to do anything. However, with Intel drivers, you actually need to rebind it. So we can try, just as a practice, we can rebind it to we can try VFIO, but that shouldn't work. When VFIO is not working, you can also enable you either bind it to the IGB driver. Those are kind of two drivers you can bind it to. I don't have the IGB. Okay, never mind. I'll UIO PCIe in generic, let's say, and I'll bind it to that driver. Essentially, to give you some context, you can bind it either to VFIO or UIO PCIe generic drivers. It's preferred to bind it to VFIO, but when it's not available, then I guess it's okay to bind it to UIO PCIe generic as well. Okay, never mind. With VFIO, you can, there is also a certain directive about, I think, unsafe MMIO, basically that this gave us error that it cannot be bound to the VFIO, but with the unsafe VFIO setting, it would be possible to bind it. But now we will work for the sake of demo with Mellanox card, and let's see, we have it already compiled. That's nice. Okay, so we will edit the Suricata YAML file. As you can see, we have the interface already here. So I'll set it to, let's say, .1. I'll set it to 8 workers and leave the defaults as are. Now let's try to run it. But the thing we forgot, and that's often the case, you forgot to allocate probably the huge pages. Okay, it was doing okay because let me check the huge pages. I already have it from the prior runs already allocated. Okay, and let's see. Here we see already that we are receiving some packets, so that's good. I've essentially grabbed the stats.log for capture statistics, and I see that capture.packets, it's already receiving some packets, but it's also, these categories signal that we are missing a lot of packets. And let's see why. When we open the performance monitor, we see that only the first core is active. And that is simply because we didn't set the CPU affinity. That's common fault. So you always need to set the CPU affinity. So yeah, we set it to yes. and we set it to the list of cores. Now I'll explain a bit just in a second why did I set it to 2, 4, 6, 8, etc. Let's try it. And now when we look at the HTOP, we see that it's running on 8 cores as it should. Now, the reason I kind of set it to 8 cores is because on multi-CPU systems, you want to be on the same NUMA node. NUMA node is a non-uniform memory access, and that's kind of how it's kind of architected in a way. When we look in supportive slide, this is our server, the green thing, and these CPU sockets are your 2 processors of your server. When you have a NIC on NUMA node 0, kind of like on one area, you want to interact with the NIC with like CPU socket or the CPU on that's the same NUMA node or on the same area. You don't want to interact it with CPU with the second CPU in a different spot, because even though you can, but there is like CPU interconnect or some path that connects your 2 CPUs together, so you can communicate with whatever you want, but it takes a toll because of the remote access. So my cores on the CPU socket 0 are kind of these the not the odd, but I think the even numbers. Yeah. The same applies to memory. When you start your application on one NUMA node, it essentially wants to allocate all its memory on RAM slots or on memory slots that are on the same NUMA node. That way you can have the fastest access rates to the memory. It's better to occupy all memory. So instead of one 64 gigabits memory, you want to probably use 8x8 memory sticks, just because more memory channels provides more throughput to your application. To kind of speed up a bit, this is kind of the architecture of the demo server and the reason why I used the even numbers. I was able to determine the CPU cores of my CPU socket 0 from either this command or the ls CPU, which I will show in a bit. I was able to check what memory slots I have occupied by listing hardware, essentially. And you can also check on which NUMA node your NIC is by kind of looking into this command. And I kind of found out that the NIC is on NUMA node 0, therefore I used CPU 0, and I tried to, use as many slots as I could, but we still have these slots free. So from ls CPU, from this command, we see that the reason why I used even numbers for this Suricata run is because they are on the node 0. I see that we got flow emergency from the traffic we are receiving. Doesn't matter because we will just adjust our settings, our Suricata settings a bit to be able to handle the settings, to be able to handle the traffic as it should. Let's see. I'll adjust multiple settings just to be sure you're doing fine. Okay, I'll enable stats interval to 2 seconds. And today we will read the stats.log file for our statistics. I'll increase the flow table to more same number. Let's say to 8 gigs of RAM memory, because we can stay within hash table size for the flow memory, but we will pre-allocate all elements there. We will also increase the memory for the defragmentation engine. We'll also increase our stream engine. These are kind of Suricata settings that you would encounter in your like AF packet setup, PF ring setup, doesn't really matter. So I don't want to spend too much time on this and rather focus on DPDK settings only. So yeah, this is set. And okay, and to kind of illustrate the bugs that you can encounter, or not the bugs, but rather error counters that you can encounter with DPDK, I'll set it to DPDK to let's say low settings, so that DPDK will be actually the bottleneck of the Suricata. These are rather small settings. I'm kind of ignoring the recommended sizes that are described here, just to illustrate what kind of errors you can encounter. Okay, so now we have Suricata configured. We can try to run it. And let's see. Okay, we are seeing essentially two different error counters, and one is I missed, and the other is no mbuffs. No mbuffs means that you don't have any mbuff, meaning like a packet representation in your software available when your card needs it. So packet arrives to the card, and now the card needs to push it to Suricata, but there are no available kind of objects in which the network card can put the packet to. So this error counter is complaining about that, and I missed error counter is complaining that the error that essentially the queue in the network, like the network interface card, is so overloaded that it cannot even parse the packet, or it cannot even process the packet, so it must be dropped. Now we'll focus on the no mbuffs, because it's quite easy to fix. We will just increase the mempool size. We will increase it essentially to, let's say, to a bigger value. We will also increase mempool cache size. This mempool cache size is a cache that each core has. So in your original mempool, you need to have at least as many elements as number of cores times cache size. In our case, 8 by 500, it's something like 4,000. So we have enough for that. And that also applies to our receive and transmit descriptors. I usually set it to the same value, even though we are only in IDS mode. It doesn't really hurt to have it allocated that way. And now let's see our stats. Okay. It seems like by increasing our mempool size and increasing the receive transmit descriptors, we were able to eliminate the no emboss counters. And now what you can do is also try to increase it even more to maybe even provide a bigger buffer for Suricata to process packets. So yeah, let's try it. There is one thing that I would like to point out, and that is with this, you have a much smaller drop rate. But with drops here, it's somehow more like you have a bigger percentage of drops. That's kind of a bit misleading, I know, but when you are evaluating your setup, you should really focus on these statistics and not so much on these, because these can get a bit off. As you are shutting down Suricata, the NIC still can receive some packets while Suricata is not receiving any, and that's why drops are kind of in a bigger, like they can get bigger than they should. Okay, so and now we want to increase the mempool even more. Let's say to 16K. We will leave mempool cache as is, because usually 511 is the maximum number, or 512 is the maximum number you can set for your mempool cache size. And unless you change it during the build time. Okay, we've increased our mempool. These missed errors, again, these are because as you are starting your device, you started your NIC, but Suricata yet still wasn't receiving packets, and that's why there are still a bit of missed packets. But as you can see, uptime is increasing, but we are still having the same amount of missed packets. Here we counted a few up there, but it's staying in place. So let's say we can say that we basically configured Suricata for this network in terms of DPDK settings. Okay. So like general tuning tips, you can try bigger settings, lower settings. It's up to you. Try it as you can. Generally speaking, bigger mempool and more descriptors will lead to more, let's say, cache misses, but it might just provide a better buffer for you. Another thing that I wanted to point out, when you have verbose logging enabled, when you are shutting down Suricata, you have extended statistics of your Suricata. Here we can see that basically the NIC directly received X amount of packets. We can see on individual queues of the NIC how many packets it has received. Unicast packets, multicast, broadcast, everything. And here you see that out of buffer, essentially, that was the error counter for Suricata when NIC was overloaded and couldn't really process any more traffic. Okay.
Lucas?
Yes, Juliana?
Sorry for interrupting you. We are a bit over the time. I wanted to know if there are any very important things that you want to say, or just suggest that we wrap up so we can read the questions. Is that possible?
Sure thing. I'll just quickly go over the frequently asked questions. I think it's very much described in the points itself. I'll just try to go over the questions itself to make sure I point out something very important. Yeah, okay, that's fine. Yeah, let's see what the questions are, and then we might just go over the frequently asked questions, just in case we have some time extra. All
right, so let's see. The first question was from Michael Savka. Okay, the question is, what is your experience in running the DPDK Suricata in Cloud SNN, like Azure and AWS, both supporting DPDK?
I haven't been able to test it. I haven't had the chance to test it directly in cloud environments, meaning AWS or Azure or in services like this. But as I tested it with virtual interfaces, it works. It should work there. If not, we are accepting PRs. We are always happy for contributions, but yeah, it should work in virtualized environments as well. Although it's good to note that, let's say I've tried it in VirtualBox, and that allowed me only one queue to be enabled. That essentially means you can have only one Suricata worker enabled as now, which can be a bit limiting in virtualized environments.
I would also invite anyone who has experience in running Suricata and DPDK on cloud environments to reach out to us. Maybe we could set up a webinar to see how that works and discuss that more. Okay, moving on to the next question.
We might just add little notes that I kind of, it's good to know that with DPDK, you cannot use arbitrary NIC. This is the first point. It needs to be like DPDK supported NIC, and that can be found, let's say, on this page. Essentially, some old hardware or some desktop network cards will just probably not work with DPDK if they are not supported. And that can apply either to virtual environments or physical environments as well.
That's very important. And it is indeed a question that we get sometimes in our chat. Folks, the slides will be available. So if you want any of the information that is there, you'll be able to copy it later on. Moving on to the next question from Vinay Reddy. When would one leverage Intel DPDK if the performance gain is mere 10 to 20%? Is it worth the effort, like cost versus benefit?
I mean, I guess it depends. I mean, if you have a lot of deployments where you can utilize the DPDK experience, then probably yes. If you have a single deployment which you care about and AF packet is running just fine, and probably, yeah, DPDK is like it can encompass a lot of stuff that's connected to it. So that might not be the case, but if you are having let's say more deployments, then it can save you some hardware. I mean, you can essentially use the hardware for a longer time, considering you can squeeze out more performance. But it's also good to know that it depends the performance benefits on the actual deployment. So I don't think it's really hard to try. As you've seen, we were able to set up 2 deployments with DPDK in just about under an hour. So if everything, even like I think it's good to try. But on your setup, if you have single deployment, probably you don't need to care that much. But if you have more deployments, then sure, go for it. I hope I answered the question.
If not, please, folks, let us know. So someone, Balachandran Sivakumar, asked about the virtual environment. What was the virtual NIC that you were using, the driver? If it was virt.io or something with sriov?
Yeah, it was virt.io. I think you can see my VirtualBox manager, and within that, it was just so it was just 8000 environment by default. But I also tried it with virt.io as the adapter type, and it was also working like that as well.
Thank you. I saw that the person got the answer, but I wanted everyone to have it. So
okay.
That's it. And Sophie Bernier says, I've seen one of your previous presentations where you talked about the architecture of DPDK support in Suricata. At the time, you were using DPDK multi-process support. Is this what you're still using in this demo?
No, that's part of my PhD work, and that was connected with DPDK prefilter, in which DPDK prefilter is the primary application, and Suricata is the secondary application. Multi-process support is not directly supported in Suricata 7.0. That's kind of my custom branch, let's say, my experimental branch. I can refer you to the implementation where secondary process is supported, but it's it's in the development. But if it can help anybody, then I can surely link it. So it would be in between. Yeah, so it's this branch 5203. I guess it's better to reach out to me, and I'll talk to you in more detail whether it supports what you want. It's probably better that way.
Good, makes sense. And folks, you can find Lukas in our forum, on Twitter, and on Discord as well. So for our last question, Andre Ten Beamer asks, is it possible to bypass traffic with DPDK like eBPF does for Suricata?
Yeah, that's kind of, honestly, that's kind of it was kind of a bit confusing for me. But with the currently you bypass the traffic directly in your Suricata. Now, is that different from eBPF? eBPF basically sits somewhere in this NIC driver, and that's like the first place that receives the traffic, let's say. But with DPDK, you essentially skip all this, and so the packets go almost directly to your application. So kind of having something like eBPF doesn't make much sense in DPDK. However, with like possible future additions that can be done to DPDK with DPDK support, is that DPDK have very good hardware support, and with DPDK you could potentially insert hardware rules to the NIC directly, and that NIC would directly bypass the traffic for you. Some NICs support this on with eBPF, like I think it's I think it starts in with M, doesn't matter, but with DPDK that would probably, like, this hardware bypass would be supported on a much broader scale of NICs. I'm trying. Yeah, I guess we can go on for the next question. I'm just trying to.
That was the last one.
Okay.
And it's almost my time. It's almost 3:30. So this was a very long webinar for, as far as Suricata webinars go.
Yeah. Too bad it's that short. All right, cannot find the direct support, but the one vendor basically supported eBPF indirectly in hardware, but with DPDK, potentially, yeah, we can support more NICs. However, this hardware's bypass is not yet supported. All right, yeah, so yeah, we'll have the slides available to all of you. I hope I passed as much knowledge as I could in that hour and a half. And I'll just, I guess, pass word to you, Juliana.
Thank you. If you could allow me to have my camera so I can talk to everyone as we say goodbye to our audience.
Sure thing. No, if I only could.
Well, if you can't, then I'll be just.
Maybe, yeah. Oh,
So, folks.
No, sorry, no camera for you.
It's fine. Thanks a lot for joining us today. Thanks to everyone who stayed this long. I didn't want to interrupt Lukas earlier because I know there's a lot of information to be shared, and this will be available, as I said, on our YouTube channel. So be sure to check it if you want to check any details. If you couldn't stay until the end, it will be there. As usual, if you have any other questions, do share them on our forum, which is forum.suricata.io, right? And we also have the Discord channel server. So do join us there if you have webinar ideas, if you have questions, if you want to contribute to Suricata, anything. We are there. We want to hear from you. We will also have another webinar from with Mr. Peter Manev in May the 4th be with you. and yeah, join us for this next one, which will be less developer oriented, more setup oriented and will be about threat hunting. Thanks a lot again. Thanks for the questions. Keep reaching out to us for future ideas, for webinar ideas. We exist because the community exists. Thanks, Lukas, for putting this all together. And
thank you.
See you another time, folks. That's it for today.
Bye-bye.
Bye.